Okay, so today I'm going to be working through using PDEPE to solve or to model partial differential equations and their solutions in MATLAB. So I say in plain-ish English because if you look at the documentation that MATLAB provides for how to use PDEPE, it is one of the most long-winded and unclear things that I've ever seen. So fortunately, PDEPE is actually really simple to understand. It's a really great function, and I think it'll probably be useful for most people's final projects. But it took me a long time to figure it out. So hopefully this will shed some light on using PDEPE and not just relying on code that we've been given. So, disclaimer, the resource that really helped me to get to figure this out is this YouTube video, which I will try to link to, but I don't know if it'll actually have the link in the AM105 website. So I put the link here in case anyone wants to go through that. This video, though, is pretty long, and it doesn't go as in-depth as I'm hoping to go today. So moving on from that. So just a quick note, PDEPE lets you solve any differential equation that you can write in this form. So you have a function of c times du over dt equals x to the power of negative m times then the differential operator on x to the m times a function, and then outside the differential operator again you have plus another function. So we have I'm going to be working through problem 5 from PSET 8, I believe. So this is asking us to understand the equation du over dt plus t squared plus 3t du dx equals 17 to the second derivative of u with respect to x. So remember that we're looking for rewriting this equation in this form, and that gives us our parameters: c equals 1, m equals 0, f equals 17 times du dx, which is how PDEPE expresses the first partial derivative with respect to x, and s is t squared plus 3t times du dx again. So with that, we will move on to MATLAB. So first I want to show that the documentation for PDEPE is actually as bad as. So we get this, which goes on for quite a long time and has lots of words that, I don't know, it just it didn't help me understand PDEPE at all. So instead, I want to be looking at these two scripts, which were given to us. Well, this one on the right was given to us by Professor Brenner, and the one on the left is what I created to solve this problem. So first, let's work on understanding the function pdx1. So in this function, if you look at the MATLAB documentation, which we just did, you'll see that it writes it out in terms of, it breaks it up into these 4 blocks. So the code that they gave us is actually just the code that MATLAB suggests that you use. So in the first function, you have PDEX1. You declare what your m is. You set your space over which you will be solving this, so it's a function of x and t. As a side note, you cannot change the variables. PDEPE only works with u, x, and t, so you just have to rewrite everything in terms of u, x, and t. If you have different names for your variables, too bad. So you have, because I've already run through this, I roughly know what the solution is going to look like. So I know that you don't need anything more to the left than -20, and you don't need anything more to the right than 100. I'm breaking that up into 300 divisions. Depending on how fast your computer is and how long you feel like waiting, you can do more or less. But this is more than enough to get the feel for what it looks like. And then t, doing only to time equals 5. That's what we need to do for this particular problem. Do it with 10 time divisions, so every half time unit it'll recalculate. Then this line, which calls the remaining functions below, and then say that u equals what this finds. So it's pretty unclear language, but you can just kind of look at it and see that see what things are doing. So then the next step is down here where you declare what your parameters are. So as we discussed from the PowerPoint, our c is equal to 1, our f is equal to 17 times du dx, and our s is that. So, which I realized I said in the PowerPoint was 17, so I just changed it so that it accurately reflects the -17. So anyway, then the next thing you need to do is define your initial conditions. So we were asked for a rectangle from -1 to 1 of height 1. So you just code that in like this. The absolute value of x is less than 1, then u0 equals 1. u0 is the initial conditions. Again, it's not your typical MATLAB syntax because you're not setting a vector or anything, but PDEPE has its own defined variables and syntax, so just believe that that works. And then else, u of 0 equals 0. And then here, they had included this, but I commented it out, which just you do by adding the little percent sign, which would have changed the initial conditions entirely, but it's a quick way to switch back and forth between a Gaussian and a rectangle, so you can see what the differences are. Okay, so and then the final thing is to determine what happens at your boundaries. So in this case, we want to look at the whole number line, so we have to define our boundaries such that it doesn't interfere. But this being MATLAB, you can't actually set your boundaries -infinity to infinity, so what you do is you set it beyond what you're looking at. So we're going to go into our main window, and we're just going to say that PL, which is your left condition, I don't know why it's P, equals -120, and PR equals 120, and those actually should have been UL and UR. Anyway, so then you see that 120 is to the right of 100, and -120 is certainly to the left of -20, so it's not going to interfere with our simulation, and we set them equal to 0 just because it doesn't matter what we set them equal to. So with that set up, we can now use this function that we've just written, or this set of functions that we've just written, to actually plot the solution that we want to see. So you say that you have three variables, x, t, and u, which are the output of PDEX1, which is the same as over here, so that's consistent. So I'm just going to open up a figure by typing figure, and then we're going to say hold, which means that we can plot multiple things over and over again. And then, and this is just a nice little MATLAB trick, you set the variable colors equal to this string or any other string. There are defined colors in MATLAB that you can make things. So there are more than this, but I'm just using 5 because it's a nice number, and these are the most clearly distinguishable colors. So we have magenta, cyan, red, green, and blue. And so I'm going to say that while the length of colors is less than the length of t, we're going to combine, we're going to keep repeating this string over and over and over again so that our string is long enough so that each value of t is corresponding to a color. And then we're just going to plot our solution u. So for every value of t, we're going to plot u versus x for that t, and we're going to assign it a color. So what happens when we run this? It takes a few seconds because of the large space interval that I'm using, and we get this nice plot. As you can see, we start with our initial condition as a rectangle, and then it quickly turns into something more recognizable as a Gaussian, which, if you follow along with our colors, you can tell the order which things are going to be sure that the trend that you think you're seeing is actually what you're seeing, which is the nice thing about assigning a string of colors. So you can see we have magenta, we have cyan, then we have red, then we have green, then we have blue, and it starts over again, and it goes down. And because we have 10, let's go through the cycle twice. So what we see here is that we have advection and diffusion, which is exactly what we expected looking at the equation. So it's spreading out and moving to the right. So the second part of the question asked us to plot the maximum of the solution as a function of time and plot the characteristic width of the solution as a function of time. So that's what we're going to do next. So we can close out of this and look at the code for part B. So we open up a new figure again, we hold it, we create 3 vectors of the same length, which is 10 in this case, which are all zeros. So then we say that for I is 1 through the length of t, so for every value of t, we find the maximum value of u for that t. So we find the peak of the Gaussian that corresponds to that t, and we assign it to mxi, so the maximum of I. And then we want to find the index, so where along the x is that, because max just returns, the function max, MATLAB function, it just returns the maximum of a vector. It doesn't tell you where it is in that vector necessarily. So we want to find the index of the maximum, which is what we do with this line. So we find where u equals the maximum, and we save that to index of I. And then we plot with a black X. So that's what this says. We're putting a black X at each point. We're going to plot T of I and the index of I. So this will plot. So this plots where the maximum is with respect to t alongside the so 1, 2, 3. So this plots the location of the maximum as a function of t and puts a black X at each location of the maximum along the x-axis. Okay, so now that we understand this code, I'm actually going to divide this into its own section so that we can run this code alone and see how it works. So we're going to run this section of code now, and we're going to see that the speed of the center gets further and further, or gets faster and faster as time goes on, which we easily saw in the original plot, which I will pull up alongside it so that we can compare and show that these are showing the exact same thing. So on the left we have the solution to our equation plotted out, and on the right we have the location of the maximum with respect to time. So we have the first one, and then second one, and then third one, and so on. As it moves on, you can see that they're getting further and further apart, which we can see here. So now that we believe that that is true and that that code worked, we can move on to our last little bit of code. So same thing, we want to create a new figure and we want to hold it. And remember, we are trying to plot the characteristic width as a function of time. So we want to say that, so remember, for a Gaussian, the width is defined as the width at half max. So what I'm doing is I am, let's say for this blue spike right here, I am taking the x value here, and then I am finding what the x value is at half of this max. So we're at 0.18, so we're looking for 0.9, so roughly about here. And then we're going to subtract this x value from this x value, take the absolute value of that, so we're finding this x value, and we're subtracting it from the x value of this peak, and then we're multiplying that by 2 to get the distance from here to here, and that gives us the width. So how this code works is we're using the find function, and we're finding where u is, we're finding the first place where u is greater than the maximum over 2. So we're finding we can't actually find where it is exactly equal to half the maximum, because this is discretized and there might not be a value corresponding to exactly half the maximum. So to guarantee that we find something, we say find where u is, find the first place where u is greater than half the maximum, which, because I discretized with 300 points, is going to be very close to the 1/2 the maximum, and won't really introduce any significant error into the calculation. So if we run this section, we see that our width is increasing like a square root function, which is exactly what we would expect from a diffusion equation. So we know that we got this right as well. So that's all I have. Yeah, this was helpful, and thanks for watching.